Hello everybody, my name is Pranav and today our session will be on discussing about types of sorting. So before coming to the types of sorting, let us discuss first of all what is sorting. So sorting is an arrangement of the data in a logical order. It can be ascending or descending, that is from smallest to biggest or from biggest to smallest. So examples where we come across this sorting in our day-to-day lives are while arranging the roll numbers of students or arranging the list of names of students or according to their marks. There are many other day-to-day life examples where we use sorting, and it is an important algorithm. Coming to methods of sorting, there are two types: internal sorting and external sorting. Internal is referred when the sorting algorithm uses only the main memory where the data is going to be stored, whereas external sorting, you find that the algorithm is using the external memory that is known as the auxiliary memory. So it is using both the memories, not only the external but both the internal and external, which is known as external sorting. In this PPT and session we are going to only discuss about internal sortings. Coming to stable sort. So what is stable sort? You can read the definition, but I am going to explain through this pictorial so that it will be easier for everybody to understand. Now I have an unsorted array which is 10, 20, 20, 30, 10, and they are of different colors so that we can identify the key. Like 10 is in the 0th index, 20 is in the first index, and so on. The red 20 is in the first index and green 20 is in the second index, and so on. That's why colors are being mentioned. Now, after the sorting is done, we can see that the blue 10 stays in the blue 10 place itself. So its index is not being changed. So before sorting, it was in the 0th index, and after sorting also, it is in the 0th index. I mean, it is not getting right side of the purple 10. It is left side of the purple 10, which before sorting also it was on the left side of purple 10. So the positions didn't change. This is known as stable sort. If we take an example, like if we take a heap sort is one type of sort where it is not guaranteed that you get the blue 10 left side of the purple 10. There are cases where you get the blue 10 right side of purple 10, where like this full array is going to be shuffled and then arranged, so you don't have a guarantee that blue 10 is going to come left side of purple 10, and here the red 20 is going to come left side of green 20. That is not guaranteed. So those kind of algorithms are known as unstable sort. Some of the sorting algorithms are stable by nature, like insertion sort, merge sort, bubble sort, etc., and which are not stable are like heap sort, quick sort, etc. I hope you understood this. So there is a definition in this picture as well. Sorting is stable because the order of balls is maintained when the values are same. The balls with blue color of value 10 appears before the purple ball with value 10. That's what I just mentioned. Going to the next slide. So why are there so many methods of sorting? Can anybody answer? Okay, the answer is in the slide itself. It's efficiency of sorting. So because we need more efficiency in sorting algorithms or any algorithm, whatever we are performing, we need more efficiency. To improvise our efficiency, we can do maximum in using different kinds of sorting. So there are three parameters mainly that is affecting the efficiency of sorting. They are time spent by the programmer to produce the code. So I take 10 minutes to write a code and I take 20 minutes to write some other code. Then I choose the 10 minutes code itself. So that is the time spent. Next one is amount of machine time taken, that is time complexity, and machine's memory taken, that is space complexity. These both are important factors that are going to be checked in if you come to competitive programming. and solving questions in any contests. These are the two main factors that are taken into consideration. Most sorting methods are ranged from n log n to n square. So big O of n log n is the minimal of any sorting. If you take any sorting type, and n square is the maximum time taken. I hope you understood. Sorry. So this is one of the cheat sheet that I have collected from a website. This is array of sorting algorithms. So there are algorithms, and corresponding to the algorithms there are time complexity and space complexity respectively. And as you can see, time complexity is also divided into three, which is best, average and worst. When do we call best? Best is when we have an array already in increasing order. For example, 1 2 3 4 5 is my array. Then that's the best case, where the algorithm has minimal to do to that array to make it again increasing order. Average is where you don't have it in increasing or decreasing. You have it in a random order, say 50 40 10 20 30. That's an average case, because 50 40 are decreasing, 10 20 30 are increasing. That's an like average case. Worst case is like when you have the array in a completely decreasing order. It's like 50 40 30 20 10. That's the worst case. We have lot many number types of sorts, and we can see that orange denotes bad, yellow denotes fair, light green denotes good, and dark green denotes excellent. We can see that bucket sort, radix sort, counting sort are all excellent in the time complexity, but we don't generally use them because they comparatively take more memory space. That's space complexity, and they also take more amount of time for the programmer to write these kind of codes. So we are going to discuss one by one in the coming slides. If we Google what are the types of sortings, we get many sorting algorithms. So these were the algorithms all what I've got, and we are not going to discuss all of them, don't worry. We are going to discuss only few of them today. That are bubble sort, selection sort, insertion sort, merge sort, and quick sort. Let's dive into the bubble sort. It works on making bubbles. Bubbles in the sense one element is compared with the adjacent element, and that comparison uh, tells us with an if statement. We are going to run this code with an if statement where aj is greater than aj of aj plus 1. Then we are going to swap the elements. Sorry. So the first for loop is actually for the passes. If I is 0, then it is referring to the first pass. If I is 1, it's referring to the second. And if I is 2, it's referring to the third pass. Next comes an nested for loop inside the first for loop, where you're going to create bubbles. That is first bubble, second bubble, third bubble. And this is the array after the first pass, and it is sorted partially. That is, one element is fixed in its position. So each pass we are going to fix each element's position. And then the if statement, as I've told you, it is helpful for checking the elements and swapping. Now let us see this first pass. So 7 is greater than 6, so it is going to swap. This is, and I forgot to tell you, this is the worst case that I've taken, because 7 6 4 3 is completely in a decreasing order, and 7 is greater than 6, it is swapping, and 7 is greater than 4, it is swapping, 7 is greater than 3 is swapping, and 7 is fixed in the end position, which is the end of first pass. This is how bubble sort works. And second pass, third pass, so on. The number of passes is actually n minus 1. That is if n is the number of elements in the array. Moving on. Time complexity. This is an important factor, the parameter of efficiency of sorting. That's why we are going to discuss time complexity of each and every sorting type. In the best case, it only runs n minus 1 times, because it's if n elements are there, we are going to run only the passes that are n minus 1 passes, and we are not going to swap anything, so that is not taken as a time take. That doesn't take any time, and it is only big O of n. Next, coming to the worst case, we are having n minus 1, then n minus 2, each pass n minus 1 swappings, then n minus 2 swappings, and so on so on. We get this tn, and we can write it as big O of n square. And similar in the average case as well. I hope you get this. Yeah, average case is like first 50 40, then 10 20 30. This is like decreasing and increasing. This is a case which is not completely decreasing or completely increasing. Next, coming to the selection sort. Selection sort works in a way where you have this left part, the green part is this sorted part of the array. It is going to sort partially in each step and going to keep the partial sorted array on the leftmost part. So I'm just going to explain how it works. Now 10 and 14 are the least in this array. They are kept in the left, and it's like highlighted as green. You can assume that there is a wall over here where left side of the wall is the sorted array and right is the unsorted array. Next, our program is going to scan in the unsorted part of the array, which is the least. The least element over here is 19. So 19 is going to be swapped with 27. You can see that 27 has come to the place where 19 was there earlier. Next, 19 is like confirmed it is that correct position, and it's going to create a wall over here. Next, scan, you find that 27 is the smallest. 27 is swapped with 33, that is just beside the wall over here. 27 and 33 are swapped, 33 comes here, and so on. The process is going to take place until all are swapped. Coming to the code part, the for loop over here, that is the first for loop, is going to keep a check of all the steps. So first when I is 1, then when I is 2, then I is 3, and so on. Each step, each value of I increments. Then for each for loop of I, then you are going to store the index in P. The index value where the wall is going to stored in P. And next, the for loop actually checks which is the least element in the unsorted array. So if aj is less than ai, that is the condition to check which is the least element, and it stores in the least, and the index is going to be changed for the next step, and swapping happens over here. So whenever we find that the least element is somewhere, we are going to swap that element. Again, coming to the time complexity of the selection sort, it's all big O of n square. So selection sort, uh, let it be average case, worst case, or best case, it's going to be big O of n square. That's because you are not stopping anywhere if the whole array is sorted. Unlike of bubble sort, it's not going to stop, and it's going to swap. Like if everything is in the correct order, like 10 15 20 25 30, is going to tell 10 is sorted, and it's going to bring a wall over here. Then it's going to find the least element in these four elements. There you find 15 is the least. Then 15 is going to be placed in that 15 itself, that is taking one step, then creating a wall over here. That process happens. So there is no escaping of any steps if it is best or worst or average. Coming to insertion sort. Insertion sort keeps the element in the left of the array keeps the left of the array sorted. So as same as selection sort, it keeps the left of the array sorted and keeps inserting the elements from the right to the right position in the left part. So if I have this array and I have 7 as the first element, now I say 7 is sorted in this subarray. In this subarray of the elements where only 7 is there, that is the subarray, and there 7 is sorted. Next, in the unsorted subarray, we have 2 as the next element. Where we are going to place that 2 is going to be judged by the code, and it should be left of 7, right? So it's going to place 2 over here, and 2 7 is the subarray which is sorted. Next step, we are going to have 4. Where should 4 be placed? That is going to be judged by the insertion sort. It's going to be placed before 7 and after 2. That's correct. It's the middle position of 2 and 7. Now we have the sorted array over there, and right side of 7 we have 5. That is the next element which is going to be inserted. Next is going to be placed between 4 and 7. 2 4 5 7 is the new sorted array, and 1 3 is unsorted. Next 1 is our target, and so on. The process goes. So you can see the code over there. Until now, which we have discussed, bubble sort, selection sort, and insert sort will have two for loops are nested loops. So we'll have two for loops, or it can be one for loop and one while loop, because it can check the condition, or two while loops, any of your choice. Now here it's going to check the condition where whole is greater than 0 and C of index like whole minus 1, that is the leftmost element, that is greater than the value. So if these both conditions satisfy, then only there is going to be an like insertion taken place. I hope you get it. So moving on, the time complexity of insertion sort. Best case, worst case, and average case. In the best case, it's big O of n. Worst and average case, it's big O of n square. Insertion sort also works similar, the time complexities works similar to the bubble sort. Now there is nothing to be inserted, like because this is a completely sorted array, there's nothing to be inserted newly. So the Tn can be written as n minus 1 itself. That leads to big O of n. Worst case, you have everything to be inserted newly. So it's like n minus 1, n minus 2, and so on to 1. So that's big O of n square. Moving on. Divide and conquer. Divide and conquer is a new logic or algorithm that is chosen because we have higher time complexity that is being taken by bubble sort, insertion sort, and selection sort. So to newly reduce this time taken, we are going to use divide and conquer. For a better runtime, we use divide and conquer algorithm. Merge sort and quick sort work based on this algorithm. We are going to discuss next what is divide and conquer. We are actually dividing the problem into two subproblems which are similar. The point is to be noted is which are similar, and then those solutions to those subproblems are going to be calculated, then combined to find an ultimate solution to the problem, actual problem. Merge sort. Merge sort is actually known as binary tree. Like it divides. It's also known as binary tree sorting algorithm, which actually is dividing the whole array into two equal halves, and that subarrays are again further going to be divided into two new equal halves. Those subarrays again are going to be divided, so it's like dividing by two. You can observe that the height of the tree is actually log n. Log n is when you get the time complexity of log n when an element is being divided by 2 and so on. So this is actually the splitting process that the merge sort is first doing. And the second process which the merge sort will do is combine. The combine actually sorts and combines. So it basically does both. You're seeing here that 54 and 26 are two elements in the subarray which are splitted before. So now they are going to be combined by sorting. So 26 and 54 is the order, correct order. So that's going to be one subarray, new combined subarray. Next 17 and 93, that's one more. So you get combinations of sorted arrays, and that are in fact combined in the next stage, and that will be again combined. So it's combining takes place recursively. So merge sort is taken place recursive way because the function is called itself inside the same function. So merge sort it's going to call itself. Now basically these are two functions which is used for merge sort. The first function actually splits the actual array into sub halves, and the second part is going to combine them. As we have seen here, the first part of merge sort is going to be taken place by this part of code, and second part of the merge sort is going to be taken care by this part of code. Now looking at the code, there is a condition over here. If n is less than 2, return. What this condition does is we are going to say the algorithm that if I find only one element in the array, the sub array, the newly sub array, then you have to return. That means stop the process over there. So it's going to return blank. That is going to stop the process over there. So this is the final answer which I want. It's going to stop. Next we are going to get the middle index, that is n by 2. N is the number of elements, so n by 2 is the middle element index. Next L is equal to malloc. We are going to feed them with this middle into size of int, and then r is the right subarray and L is the left subarray. For easily recognizing them, I will just named L and R. Next, for I is equal to 0, I is less than mid, I plus plus. So if until the mid actually comes, I have to place them in left subarray, and after the mid part, until I get the end of the array, I have to place them in the right subarray. So creating the left subarray and creating the right subarray. Next, after this process is done, we are going to call again So this recursion takes place from here. So this is first recursion, this is second recursion, this is third recursion. So there are three recursions taken place in this example what I've shown. In fact, the right part actually recursion takes place four times. 1, 2, 3 and 4. There are 5 levels, so there are 4 recursions taking place. And after it comes to this stage, you can encounter this line of code, and then it comes back. Then this statement comes into picture, the merge function. We are calling the merge function, and we are giving the array, left subarray, middle index, right subarray, and n minus middle. So we have a 4 in the left subarray and 5 in the right subarray. We are going to give those numbers. Next, after calling, what we do is we are just initializing some integers like ijk to 0, and we have written a while loop. A while loop is for checking whether I is less than left and I is and j is less than right count. Then you have to run the loop. Sorry. Yeah. So what is left count and what is right count? Left count is the mid that I have given, and right count is the n minus mid. Until I is I is being incremented and j is also being incremented. Until all the elements are done, I need the while loop to be running. There, if I find left is actually less than right, then I have to make a of k plus plus is equal to l plus plus, li plus plus. That means the element of a, the array, the actual array. There I am going to substitute with the l plus plus, li plus plus item. And if it is the other case, then I'm going to take the element from the right subarray. The elements from left subarray and right subarray are actually getting substituted in the actual array, that is capital A. That is happening in this while loop. And next, while I is less than left count, the same is written again, just in case to check. So this is how the merge sort works. I hope you all understood the code. If there are any doubts, you can raise your hand. Okay, cool. There are no doubts. Okay. Let's go to the time complexity that we have discussed earlier as well. Now for merge sort, it's time for merge sort. Now t of 1 is equal to 1. Yeah, that is okay. Now t of n can be written as, we are splitting into two subarrays. That means we are calling the recursive function two times. That is one for the left and one for the right. As you can see in the code as well, we have called merge sort twice. That is recursion of twice. So it's t of n by 2 into 2 plus, and what we are adding is we are adding the merge function, how much time complexity the function merge is going to take, that is n. As we know, because n times there is substitution in the main array. A is the main array, and elements from L and R are being taken n times because there are n elements. So Tn can be written as this. Now going down further, what is Tn by 2? In the recursion process, we are going to calculate this. That is 2 into T of n by 4. Okay, this is n by 4 actually, because we are already divided the number of elements into half. So we get 2 into T of n by 4 plus n by 2. N by 2 is for the merge function, and adding all these we get n plus n log n as t of n. That is actually big O of n log n. Yes, this is true, because merge sort, any case, let it be best or average or worst, we get n log n. I'm going to summarize this merge sort in short, saying that merge sort is using the logic divide and conquer. True. It is using the recursive algorithm, so it's calling itself. Then it is stable. As we have discussed, what is stable? When there is key, when there are two elements with the same value and they are not shuffled after being sorted, then we can say it is stable. And here in this algorithm, there is no rigorous shuffling of the array, so it's stable. Then time complexity for any of the cases n log n, space complexity is O of n. That's the summary of merge sort. Going further, we have our last type of sort which we are going to discuss is the quick sort. So quick sort is also known as partition exchange sort. We call it as partition exchange sort because it is going to do some partition, and it's going to like after splitting into two, it is partitioning into two, it is actually sorting there itself while partitioning. So that is the reason behind this name. So it works by the partition the array to be sorted, and each partition is in turn sorted recursively. So it's like the merge sort with but without two functions. It's doing in the same process. Coming to this array, like quicksort is a little bit tough to understand what it is doing, so let's keep our mind here. Now there is this element known as pivot. Pivot is going to be chosen by the quicksort every time. That is the reference element. For example, in this it has taken 6. Now 6 is the reference element, and with respect to 6, 6 is going to be placed in the right side of the array and as the starting element. Now whatever are less than 6 are going to be placed in the left subarray, and they are going to be 3, 2, 5, 1 from this list, and greater than 6, which are 9, 7, 12, that are placed after 6. Now we can have a clarity that left of 6 is lesser elements and right of 6 are greater than 6 elements. Next, the pivot is going to change, and there is a new pivot for each subarray. That's 3 for the left and 9 for the right. So because 3 is pivot for the left subarray, it is going to be placed at the starting of the right array, and 1, 2 and 1 are going to be transferred to the left, and 5 is going to be transferred to the right. Similarly, 9 is the pivot, so 9 is going to come to the subarray of in the right side. 6 and 7 are going to be in the left subarray, and 9 and 12 are going to be in the right subarray. Finally, there are 4 pivots, new pivots taken, that's 1, 5, 6, 12, and these pivot corresponding to them, the array is getting sorted. Now you might be thinking how the pivot is chosen and how this sorting algorithm is taking place in the quicksort. This sorting is little different from the rest of the sorts. So coming to discussing that, now pivot is chosen 3. I say the algorithm says to keep the pivot on the right hand side of the rest of the array, and it's actually swapped with 0, the rightmost element of the array. Now what we do is, item from the left, that is to be noted, item from the left is larger than the pivot, which is larger than the pivot. So if I come from left of the array, that is 2, 2 is not larger than the pivot. Then coming to 6, 6 is larger than 3. That is why this is kept as a note. Now item from the right, that is smaller than the pivot. From the right, in the sense it's not excluding the pivot, so it's 1. 1 is greater than 3. True. So this is to be noted. Now the both noted elements are to be swapped. So it's 6 and 1 that are to be swapped. You can find in the next array it is 2, 1, 5, 0, 8, 7 and 6. So they are swapped. Now again doing the same thing from the left. 2 is not greater than 3, 1 is not greater than 3, so it's 5 greater than 3. We are going to note 5 from the left, from the right. First 6 is not less than 3, 7 is not less than 3, 8 is not less than 3, so it is actually 0 less than 3. That is to be noted. 0 and 5 now are the elements that are noted, so they are swapped, and this is the new positions. Now we are going to do this process again, but this time we are actually getting from the left side, we are getting 5 is the greatest element, and from the right side we are getting 0 is the lesser element than 3. But if I see that from the left, when I started, the element is on the right side of the item which I found from the right. You got that right? So if I check the item from the left which is larger, it is actually right side of this element. If we get that when index of item from left is greater than index of item from right, then you have to swap the 3 with the item from the left, that is 5. So this swapping will actually be the final step of this whole process. Now we can easily check that 3 is the actual pivot which we chose, and now we have the elements left of 3, that is 2, 1, 0 less than 3, and next 8, 7, 6, 5 greater than 3. Now we can't check this order like 2, 1, 0 or 8, 7, 6, 5. We don't generally get it in any order, but we have a guarantee that less than 3 elements are on the left of 3 and greater than 3 elements are on right side of 3. Cool. Now coming to the code. This is the quick sort function. I'm going to initialize some integers. First thing, I'm going to check if low is greater less than high. Then these commands should be run. So what are they now? Yeah, now I have just told you in the previous slide itself that if there are elements which is like which is selected as a pivot, and pivot is if the element from the left is, yeah, these are the two conditions: item from the left that has to be larger than pivot, and item from right that has to be smaller than the pivot. Those two conditions play an important role in this code. So the whole process that I have told you theoretically has been written in the form of code. I hope you got this. Yeah, now coming to the time complexity of quicksort. Quicksort has the best time complexity as n log n, average time complexity as n log n, and worst case time complexity as n square. But in merge sort it was n log n even for the worst case, but in quick sort it is a different case, because when we pick the minimum or maximum as the pivot, then we have to go through each and every element. So if the pivot which we have chosen as the maximum or minimum, then we have to go through this each and every element, and it takes n square amount of time complexity. So check yourself. Coming to the first question, you can just read the question and raise your hand if you have found the answer, or you can just unmute yourself and tell the answer. So it's this is question is basically on quicksort that we have just discussed earlier, and this is a gate question which I've taken so that you can get to know the toughness. It'll be a practice for gate. Yeah, yeah, right. It's 2 by 25. Yes, that is the answer. Yeah. So the worst case, when does the worst possible location that can be seen is when we have chosen the pivot as the maximum or minimum element of the array. So those are two cases, two positions where I can choose out of 25 positions, that is 2 by 25. So the answer is 0.08. Great. Next question is this. So they have asked a simple question in 2016, that is just direct question. Yes, perfect, perfect. The answer is 4, correct. So we can refer this table, and it's like simple to memorize this table as well. So quicksort actually runs on n log n times for best and average, and they're asking for the best itself, so it's n log n. Next, for the bubble sort, it's actually n, it's not n square for best. Next, for merge sort, we know in merge sort all cases, for all cases is n log n, it's never n. For the fourth one, insertion sort, the best time is only big O of n. That's correct. So answer is fourth option. Good, good. Next, coming to the third question. Yeah, the solution is already on the PPT. Okay. So what is the number of swaps required to sort n elements using selection sort in the worst case? So we know selection sort takes big O of n square to sort a worst case. Yeah, to sort by a selection sort a worst case, that is the decreasing order array, we have to take big O of n square, but we generally get confused by that answer big O of n square, that is option C. But they have asked in a tricky manner, what are the number of swaps that are required to sort n elements in selection sort? So in selection sort we are going to sort n times in the worst case, that's why big O of n is the correct answer. This was like little bit tricky but answerable. Okay, for further info I have given some links, so you can just refer to them. And the first link is actually a YouTube video, which is of 6 minutes. He shows, okay, let me show the video. We have time, let me show it.